This lecture is an introduction to item response theory. For more information, or if you're taking my courses, please review the items module from NCME from Hamilton and Jones that talks about the differences between classical test theory and item response theory. You can also look at Hamilton, Swaminathan, and Rogers' older text, The Fundamentals of Item Response Theory, Emberson and Rees's Item Response Theory for Psychologists, and Ayala's The Theory of Practice of Item Response Theory. I used the first manual module in our introductory course in educational measurement, and I used those other textbooks as some of the supporting texts in my item response theory course. When we are talking about the theory in item response theory, we mean this in a non-traditional sense. That is, it's not a paradigm that explains why a person responds a specific way or how they decide to respond, but it's a general framework for connecting observed variables to latent variables. That is, we have items on a test or questions on a survey that we're trying to connect to the underlying factor or concept. We've discussed some of these things in a general framework of true score, universe score, or ability score. We don't ever touch or witness those things directly, but we've used items in classical sense to make a statement about someone's true score. We're going to expand on that idea. In item response theory, we have models. So these are used for a specific theory. We use our models, which are typically statistical models. And just as a sort of reminder, or if it's new to you, models are not perfect. We use statistical evidence to determine if a model is useful. When discussing our models in item response theory, we're dealing with latent variables or constructs. We can think of them as factors from a factor analysis model. But now, instead of a continuous measure as our manifest variables, we have items, which are categorical. True score theory, when we think about that as a model, is that it's at the test level. Whereas for item response theory, we're able to test our model at the item and person level, and we discuss things as theta is now our ability, and difficulty is transformed a little bit here from our p-values from classical test theory, but it still could be useful to start thinking of them as p-values, and then we'll see how they adapt to the normal distribution. When I discuss unobservable measures, if you're not familiar with factors or constructs, we could use the example of optimism. One here might think of defining optimism, that it's one's expectation of a positive future experience. But we don't ever touch, see, or feel any tangible optimism. Instead, it's an underlying latent construct, and we witness things, or people say things like they are highly optimistic. Maybe that they have low expectations of very low optimistic expectations. So we witness things often if we're asking questions on a survey. We may have responses to a survey. Those responses to a survey are not actual optimism, but they show indications that of someone's disposition in optimism. In general, we can think about a latent variable or construct. Could be any unobservable phenomena. Mathematics achievement, language proficiency, cognitive ability, intelligence. This is interesting. We don't actually, we're very familiar with IQ tests, but you never see IQ or intelligence. You just see the results of the test and items. A black hole, we could push our limits here into the physical world and say we see all of the manifest variables swirling around the black hole, but we don't actually see through the event horizon. Determination is another latent variable. Happiness, and Thomas, my son, makes me happy. Manifest variables, on the other hand, when we think about optimism, in order to measure optimism, we need to actually examine behaviors or tasks that infer the existence of the unobservable latent variable. So here we see our turtle being very optimistic here, laying on his back. Operationally, we could define, for example, our latent variable. We can collect data as observations. We could have self-reports. We could have questionnaires, all related to which are manifest variables related to our idea of a latent construct. Relating manifest variables to latent constructs, we can use some sort of scaling. And really, in this course, we're going to be starting to think about item response theory, which will certainly come in handy for this. So why should we even change from our classical test theory measures? Well, classical test theory has a lot of limitations. First, we can talk about the separability of examinees and test characteristics. Examineability depends on items that are selected for our test. As we say, true score for students are tied to a particular test. And our item indices depend on the people that we chose. So our item difficulty, whether they're easy or hard, depends on the ability of the students. We can say that classical statistics are sample dependent, and they depend on a specific test form that we've selected. We can think of item and group dependency in a short little example. So imagine field testing items for students at the George Washington University in the freshman year. The test of proficiency in a subject area was piloted early in fall and then late in spring, would provide different results and would be a different population. So you can think about introductory freshmen as novices, and we can end of year freshmen as experienced or experts. The difficulties of the items would shift and would be tied to the populations that we chose, whether they be novices or experts. Often we have different tests or test forms that we're trying to compare, and this can be a hard comparison. We could have differences in ability, in error, and precision. You can think about our classical discussions of things like parallel and tau equivalent forms. They differ in difficulty, maybe be very difficult to compare, and it's difficult to resolve in classical test theory, and we often don't even believe that we have parallel forms, and it may be hard or impossible sometimes to demonstrate so. Here are some other issues that come up with the differences between classical test theory and item response theory. For more information, please see some of the texts that I mentioned on the first slide. Our standard error of measurement is assumed to be the same for all participants, so we have test that is unequally precise for examinees with different abilities. This is okay actually in the middle of the distribution, but it can be extremely erroneous at the extremes. Our test, this classical test theory, is test-oriented, and we don't necessarily know that much about our items. Does not take into account difficulty of items when scoring. It's less than an ideal solution, as I mentioned, for equating, but also for bias and adaptive testing. And it's not falsifiable. We can't prove classical test theory to be wrong in the same way we can item response theory. So what that means is that in item response theory, we can look to see if our model fits, and if it doesn't fit, we can select a different model. In classical test theory, we're just stuck with it because we chose it. Some desirable characteristics of an alternative theory to classical test theory would be that item characteristics are not group dependent, scores of examinees are not test dependent, item level model and not just a test level model, that we don't require strict parallel forms for reliability, especially when we don't believe parallelism exists in those forms in a strict sense. We would have measures of precision for examinees and the overall test. These desirable characteristics are those of item response theory. One should note that these characteristics really only occur when the model fits. So assessing your model is important. So what is item response theory? We mentioned before models. Here we'll call it a mathematical model that relates observed scores to unseen parameters in the model. We can put items on a scale by their location. That location we'll call difficulty. Often we give it the lowercase b symbol. We can call person ability theta. There's the symbol for theta. And we place them on the same scale. So it's a mathematical model where we have items located on the scale and persons located on the scale. Where we locate the items, we call it difficulty, and where we locate the person, we call it a person's ability, or theta. This model provides the probability of a correct response to an item given a person and item position on that underlying continuum. So we locate persons and items simultaneously on the same scale. IRT, we can have two basic principles to start with. The performance of an examinee on a test can be predicted by factors that are called latent traits or ability. We see theta there again. This relationship between examinee item performance and the latent trait can be modeled by a monotonically increasing function that we call an item characteristic curve or an item characteristic function. Some of the strong assumptions in item response theory are local independence. After taking ability into account, we should not see a difference amongst our persons. Unidimensionality, really we mean correct dimensionality. So if we are using a one parameter model, such as the Roche model, it assumes that there's one dimension. We should have one underlying trait that we're measuring. Item characteristic curve should have a specific form. We can assess that form, and it's falsifiable. IRT may or may not be the appropriate method to use, or at least that model, that mathematical model may be incorrect, and we could go to pick a different mathematical model. When the model fits is when we have all of those desirable characteristics I mentioned earlier. Like, we can talk about them as invariance, our ability from different sets of items. We will see that difficulty, ability from different sets of items will be the same, and that item parameters estimates from different groups will be the same. This is very nice. So that means if you test ability on different items, we will be able to equate much easier back and forth in different forms, or in using computer adaptive testing. When we consider local independence, if we were to hold ability constant, our performance statistically should be independent. So when we count for ability, no other relationship exists. Ability are the only factors in the latent space. Assuming our unidimensionality holds, then we can say that our latent space has one ability. We can consider this as a joint distribution. Here we see a joint distribution. We have item 3 and item 4. The plus means someone got the item correct. The minus means they got it incorrect. And we can see the proportion of people getting an item correct or incorrect. The marginals, which are on the far right side, is 0.4 and 0.6. That is the marginal to get item 3 correct or incorrect. And item 4, we see 0.2 and 0.8. 0.2 is correct for item 4, and 0.8 is incorrect for item 4. So our marginal should be sufficient to explain all of the other information in the table. So it should explain 0.2, 0.2, 0.0, and 0.6. We can see that if we cross multiply 0.4 by 0.2, it does not equal 0.20. So something else could be impacting ability. Here we could see if we were giving a driving test, some of the things that might distract you, wherefore your ability in driving would be dependent on your ability to drive while you're drinking coffee, talking on the phone, and using what looks like a very old smartphone. So if we have independence, we can see that our joint distributions, when we cross multiply them, should equal the distributions in each cell. So here's the same marginals, and we see that 0.4 times 0.2 does equal 0.8. We could go through and do each one of those calculations. So we can see that we're very focused this time on ability of driving, as an example, without any other distractions or any other things that might come into play. Unidimensionality. One ability should be measured by a set of items when we want our test to be unidimensional. We never believe it's strictly met, but we can examine model fit indices to see how close to our model is to being unidimensional. Typically, we want single dimension when we're looking one single dominant dimension. More than one ability, there's other tests that we could use, other models, that we could use. We could use multidimensional IRT. Some sort of mixture could be used, maybe in a psychological setting. And there's hierarchical modeling. So there's many other options, both in item response theory and other latent variable modeling. Because we're dealing with latent unobservable variables, we need to set the scale of measure. The scale itself is arbitrary. We're going to care a lot about the relationships amongst the scale. You can think about this like a normal distribution. We can fix or set the latent values. Typically, someone fixes to have theta as a normal distribution where the mean, mu, is equal to 0 and the standard deviation is equal to 1. It becomes very easy to transform, and it's a common scale. And we have numbers and values around 0, plus and minus 0. We could set this to another scale if you wanted to. You could set it or just transform that 0 to a scale that has a mean of 100 and a standard deviation of 15 instead. Item parameter values depend eventually on the scale that you set to theta. So the item difficulties that you get in other parameters will hover around the scale that you set. And then you'll be able to tell the difference between those items and persons will be a relative measure. The one parameter logistic model in item response theory, we're going to look at the item characteristic curve. It's a mathematical expression. We can say that we have a probability of a person's success on an item connected to the underlying trait. Here we'll call the probability of success, will have a symbol of X, and the underlying trait a symbol of Y. You could think about this as a logistic regression function. So with item performance predicting examinee ability. This is a classical model. This is the Roche model. We have one parameter of interest that we care about, which is item difficulty. Technically, there's two parameters in this model. We have item difficulty and person ability. Person ability is theta. Item difficulty is B. But we define models by the number of parameters they have for items. So here we see in our model B sub I. So we have just parameters around difficulty. So it's a one parameter model. More specifically, this is a Roche model. The one parameter model, because the number of parameter items and item parameters can change the characteristics of the logistic function, and we'll see that later on. Probabilities that are conditional on theta. When we discuss probabilities, we're discussing usually the probability that someone gets an item correct. So correct is coded as 1 and incorrect is coded as 0. Here we see that 0 is less than or equal to the probability of theta, which is less than or equal to 1, and that the probability of theta is, we're going to be discussing that as equal to the probability of your response conditional on theta. Here the mathematics of the one parameter logistic model just has been altered a little bit so that just the parameters are seen one time and in the denominator. We have theta again in our model, that's the person ability. We have B, which is an item difficulty. A is a constant in this model, so we could think about setting it to 1. A we'll see later on is a discrimination model, but here both in the Roche and the one parameter model, we want to have a single parameter for that slope, for that discrimination across all items. And if we want to fit this to the normal OGI, we can just multiply. We can see we have that multiplication of 1.7 in our model. This is just a simpler version of that without that 1.7, because often we just can use the logistic form because we care about comparative, comparing people to items as on the same scale. When we first encounter a logistic model, some of you may be having difficulty with the mathematics, and that's fine. So let's break it down to the simplest form. We have the difference between a person's ability that we call theta and an item difficulty, B. So we have a person, and we have an item or task that they may be performing. Here we see a person, and we see a weight. We can think about theta as your underlying ability to lift weights, or lift things in general. And then each item laid out in this case would be a weight of a different measure. So you have a 20-pound weight, a 40-pound weight, a 100-pound weight. we can think about that our ability, if we know something about your ability, it would help us predict which weights you could actually carry or lift. Here we see a weight that may be too heavy for an individual. Their ability may be starting to push their furthest levels of ability. And then we see on the right, someone well within their ability level lifting a heavy weight. I mentioned earlier the normal distribution, that we set our theta scale to have a mean of 0 and standard deviation of 1. So for now we can just think about that as the normal distribution, which has all of those nice properties and area under the curve that we could be very useful for us when we go on to describe information about items and persons. The one parameter logistic model we've seen mathematically. At the bottom you can see the mathematical model for this. Here we can see it visually. Some of the properties are that it's monotonically increasing. It's continuously increasing. It is asymptotic. It approaches 0 and 1 but never reaches 0 and 1. And it goes on to positive and negative infinity, even though I just have plus and minus 3 because those are typical values that we tend to see when we center our test around 0. It technically goes on to positive and negative infinity. Bringing in the idea of the normal distribution, we can see that we have our item characteristic curve, that function. Theta we could think about having set at 0 with a standard deviation of 1, so we can think about that red normal distribution also going to positive and negative infinity as overlapping. That's where people are to start, at least. On the left hand side of our graph here we have the probability of a correct response, and on the bottom we have the latent trait centered now at 0, standard deviation of 1, and on the left hand side it goes from 0 to 1, your probability to get an item correct. You can consider our item characteristic curve a lot like our logistic regression models. If you go back to your introductory regression course, you can see that you have in a logistic function something that looks like a sigmoid function like this. And when you consider your traditional ordinal least squares regression with a linear linking function, you see that there's a line there. But this line is helpful for us to think about the slope and centering our item characteristic curve. Instead of our line continuing straight on forever into values which would be impossible above 1 and below 0 for probability correct, we have our logistic function which is continuously approaching 0 but never reaching it, and approaching 1 but never reaching it instead. But I find it helpful to compare our item characteristic curve and the mathematics of that to our linear models if we're having a little bit of problem understanding what this function means. So let's set up an example of a one parameter model where we have one item, its difficulty is located at 0.5, which means at that level we have a 50% chance of getting that item correct. This is a binary one parameter logistic model. We say that the difficulty or item location is at the point of 0.5. This means that B equals 0.5, 50% chance of getting it correct. The item characteristic is difficulty. And we would set that, well, we would find that B is centered at 0. So when we say that it's 50% chance of getting that item correct, that is for a person with an ability score of 0. So the B, the item, is located at 0, and theta, the person, is located at 0. We'll come back and show more examples of item locations and person location. Our model is also monotonically increasing, continuously going up, and we notice that the point of inflection is at B, so that changes the rate of change from increasing. Now the rate of change is decelerating, but constantly going up. So from 0, we see on the far left-hand side, it's approaching 0, and on the far right-hand side at 3, it's approaching 1, but never reaches it. Even at the value of 10 or 1,000, it would never actually reach 1. It would just be very, very, very close to 1. So let's come up with an example. This is an item that was pulled from an analysis. We see that the item, the 50% chance of getting that item correct, is at negative 1.2. If we have a theta of negative 1.2, we would be located at the same place where the item is located. Whereas if we have a theta of 1.5, we have a much greater chance of getting this item correct. So if we have an item which is located at B, its item characteristic, difficulty, it's not 0 this time. If we have a theta of negative 1.2, we still have a 50% chance of getting it correct. But now we have a theta of about 1.5, we have somewhere around a 93-95% chance of getting that item correct. So where you are located, your theta value is on that underlying continuum, will help us understand and make a prediction about whether you get that item correct or incorrect. Here, at negative 1.2, 50% chance of getting that item correct. And at 1.5, when your theta is 1.5, higher than that item, much higher than that item, you have a very good chance of getting that item correct. So in item response theory, I've mentioned parameter invariance when the model actually holds. So it shouldn't matter which of these two distributions we use, we should still be able to get the same item characteristic curve. You can think back to our proficiency using subjects that are piloted at GW in early and late spring. If item response theory truly holds, we would still see that we would be able to get the same item characteristic curve regardless of time period that we use that item on. So we don't have one item on our test, we have many items. Here's 4 items laid out for us. Our red item has a -2, is centered at -2, is 50% chance of getting that item correct. That's B1. B2 is at -0.5, B3 is at 0, and B4 is 1.5. B4 is like the purplish blue one on the far right, and B1 is the red one, -2 on the far left. But we are defining those items by where they are located at the 0.5 chance of getting that item correct. Only difference here is in difficulty. So our 4 items we have on our test are different locations, but all have the same slope, all have the same discrimination. So we put a 5th item on this scale, and we'll move that item back and forth to see that these slopes are all the same. We move it further up toward that purple one, we see that it mirrors that slope pretty well, and we go down. And the idea here is that we might change the location, we might change where that item is on the scale, but we don't change its slope, we don't change how it discriminates amongst persons. If we were to put persons on this scale and locate them at -1, 0, and 1, we could start saying some things. Let's take the person at the -1 theta level, that line on the far left. They have, almost no chance, very low probability of getting the most difficult item correct, which is that purple one. We see maybe like 0.2, 0.3. It goes up. By the time they get to the green item, they have about a 30% chance of getting that item correct. The black item, we just slid up and down the scale, about a 50% chance of getting that item correct. And then we get up to the red item. Well, they have almost a 85-90% chance of getting that item correct. Where the person with a +1, they have about a 30% chance of getting the purple item correct. And then they start getting up toward 85 to almost 99% chance of getting the rest of the items correct. So overall, we would expect person with the theta value of 1 on this simple 5-item test, they're probably getting about 4 out of 5 right. Whereas the person with a -1, they're probably getting 1 to 2 items correct on this test. And we can see, again, just as a reminder, those lines represent our theta ability. From a ROS perspective, there are certain characteristics we want from our measurement model. We want specific objectivity. Think about relative locations of objects and persons on the underlying continuum as sample independent. So we can compare 2 persons or items only using the parameters associated with those persons or items. We have separability of parameters. We estimate one type of parameter without reliance on the other. We can say we have a sufficient statistic. For theta, we might sum over b, and for b, we might sum over theta. So you can think about getting theta values, a sufficient statistic. We can sum over b, and if we do that, we have some sort of total score. Limits, we cannot control for guessing. Everything has equal discrimination, which may or may not be important for your your test model, but it can be vital if the model doesn't fit. So our nice qualities here only actually, for separability of parameters, is only if the Roush model actually fits. We move from the one parameter model to the two parameter model. We call this the Birnbaum model. It's not named after Birnbaum. Our new parameter, we call A, it's discrimination. We can think about it as the slope of our model. B is the location parameter, still at 0.5. This may be different than the one parameter model since we're changing the slopes. In practice, just to note, the one parameter and two parameter models should have at least an ordinal transformation, be ordinally related. Items can relate differently to the latent trait, and they may have items differentially revealability. Here's our mathematical expression. The difference here from before is that now A can take on different measures. A is our discrimination, so we don't have one A set for our whole model. We can have many A values. Here's an example of three items. All of these three items are located at 0. That is, each of these items, if you had an ability of 0, you'd have a 0.5 chance of getting them correct. But we see they have different slopes. Slope A is 0.5, slope A1 is 0.5, A2 is 1, and A3 is 1.5. So 0.5 is that green and 1.5 is that purple. We see that as you get a larger slope, you get a steeper slope, and as you get a smaller slope, as it were to approach 0, you would start to flatten this thing. As you increase the slope, it begins to discriminate well in a neighborhood. We can think about this locally. So if you have an item that has a very high slope, persons around it are easily discriminated whether they would get the item correct or incorrect. When you have a shallow slope or a decreasing slope as it approaches 0, you don't locate persons well. You don't discriminate amongst persons well. Here's just our slope or item characteristic curve at B is 0.25 times our slope. Here again is a two-parameter model with 4 items. We're going to put a 5th item on here. And we're going to slide that item up and down our graph so we can see how it compares to other items. Notice if you have an ability of 0, not only does the item location matter, but the slope matters as well. If you had persons around the value for the green item, someone that has a lower ability around even as far down as 2 still has over 20%, negative 2, still has over a 20% chance of getting it correct. Whereas the person all the way up at positive 2 now has maybe a 95% chance of getting the item correct. And when you compare that to some of the items with steeper slopes, you can see that there's a sharp difference between where they would get that item correct. So even an item located further to the left, B1, the difference here is 0.5, and then immediately, even at -1, because the slope is so steep, people have like a 95% chance of getting that B1, that red item, correct, because that slope is sharp versus shallow. Our 3-parameter model is useful because now we can incorporate guessing. C is our guessing parameter. Some people call it pseudo-guessing. Our ICC, our item characteristic curve, does not go to 0. Now it goes toward the guessing. C is technically the probability of a correct response for a person with the lowest ability level, as far over to the left of our curve as you could get. Here we now see items with different guessing parameters. C equals 0.25 for the green item. B1 for B2, that purple item, is 0.05, just a 5% chance of getting an item, guessing that item. And item 3 has a 0. It just looks like our one parameter, looks like a 1 or 2 parameter model. One parameter model, considering all of the slopes are set to 1. If someone's at 0 ability, we do see that there's a slight change of what we're talking about when we talk about the location of an item. We have to account for that guessing. An easy way of thinking about that is you have to add in half of a chance of guessing to that model. So our C parameter, we now see that a person at 0 for the B3, the black item, has still a 50% chance, but for B1, they have a 62.5% chance of getting that item correct, because they could also be incorporating in a guess to this item. Here's the mathematical formula for that. Some advantages overall. The Roush model is really good for scaling. We sort of build our items to conform to the Roche model. So when an item doesn't fit the Roche model, we remove it. For the 2 and 3 parameter models, we're usually talking typically more about model fit. We believe in some of the issues of discrimination. We look at the 2 parameter model, and in 3 parameter model, we want to incorporate in guessing. We have to estimate parameters like one would do in a logistic model or an ordinal least squares model. You still have to estimate the parameters you're going to use. We want to know what item difficulty, ability estimates are, item fit. We're going to be using some methods like maximum likelihood estimation. There may be Bayesian methods we use. We have programs like Bilog, Multilog. You could do this in SAS or R or Python or Stata. Now, what I'll say is in this video, we're not going to go through that process. I teach a item response theory course, but as an introduction, it's just good to know that we have different software packages that are available to us and different methods of getting to those item parameters and person parameters. Also, for more information, go back to those textbooks I mentioned at the beginning of our talk. Knowing if your model and items fit is important. Classically, we've done chi-square measures. You can look at empirical versus model fit measures. You can look at model level of fit, both globally and locally, person level, item level fit. All of these things are discussed in a more advanced topic in a more advanced course. But again, I'll refer you back to maybe more of those textbooks that I've mentioned earlier by Emberson and Rees and Ayala separately. But it is important to test our models. So we'll take a look at least at some empirical evidence of looking at our models. We could plot empirically our data versus our model. Empirically, we could take the item characteristic curve that's derived mathematically. We can look at proportion of examinees correct response at a given theta level. Our model item characteristic curves are based on all of the parameters. You can think about a regression, the predicted, the line itself versus where someone is actually located. So here is an item response theory characteristic curve for item 1. We see the black line is again our plotted item characteristic curve mathematically, and the red line are where people are located actually on that item. So that's their probability. It's actually binned persons. I'll get that into more of that in the advanced course, but you can look to see persons at those different points where they're actually located. And, you might note that this is not distributed throughout the whole scale, and that this item is only, I think, generated on like 50 participants. So it's a very small group. We don't expect great fit with small items, although you can get often pretty good fit with a 1 parameter model around 100 persons is not unreasonable. Our item response functions are in characteristic curves. In those comparisons, I'll show you a couple others. We might see a couple here that look reasonably good, and a couple here that look like, they're just flat. Like item 1, in this case, is just kind of, I don't know, what's going on there. Item 2, we see that although it's not a lot of people, we're starting to see the form of a slope, we're see the form of difference discriminating between higher and lower ability. Here's some characteristic curves I pulled out of SAS. We can look at the information related to items. So just like in classical test theory, when we look at variance, we look at information around items, we can say how much information does an item provide about a person at a certain ability level, and we can plot that. So here we can see that for item 1, we have the most information about people around, I don't know, close to negative 1.5. And for item 2, it's probably around, around a value of 1. People around 1, we have a lot of information about. And for all of these, as you get out towards like -4 and +4, you just don't know much about that person. What that means is that items that are sort of centered around 0, they give you the most information. Their difficulties are around 0. They give you the most information when they discriminate well around 0. But when somebody has like an ability of +5, a ridiculously high ability if an item is around 0, you don't know anything about it. Those people are always getting those items correct. So, but if you were to somehow target an item around that person, you would have more information if you gave them multiple items, or as you give them multiple items. So our maximum information is around difficulty. Our item information function, here's some realistic looking item information functions from a test that we generate. We can see that item 1 and item 2, well, they didn't do such a good job of discriminating, of giving us information. Those were those ones that were kind of flat and the actual data wasn't really discriminating anything. And items 3 and 22 on this test discriminate very well. They actually show a difference between high performers and low performers around their difficulty. Poor performance and good performance. So we want items that look more like 3 and 22 and less items that look like 1 and 2. Our test level output, so we don't just have item level or person level information. We have test characteristic curves or test response functions. It's how the test functions as a whole. We have test information functions, so we don't just have information around items. We have how much information the test provides for as a whole. We can have conditional standard errors now, just not standard errors at one location on our test or for their overall test, but we still want to talk about it as an overall test so we can see how much we can discuss the error of measurement conditionally. We can look at distributions of theta and item parameters, and then we can map item and person map together. So if we were to have 11 items on a test and sum them together, and that all of the test items here are 0, we see that the overall test characteristic curve is at 0, and that you could get between 0 and 11 items correct. And if we were to take someone at about a -1, they're probably getting less than 2 items correct, whereas somebody at a 2 is getting almost all 11 items correct. And at 0, it looks like we're getting probably close to about 5 items correct. You can think about those 11 items all stacked at 0. So we have 11 different item characteristic curves stacked up to get our test characteristic curve. Here's a full test characteristic curve. This is for 50 items. In practice here, we see that it approaches people getting about people getting about 11 items correct, and people getting about 50 items correct. If you have a 3, you're probably getting like 49. Theta is 3, you're probably getting about 49 items correct. And if you have about a theta value of, I don't know, -1, maybe you're getting less than half the items correct. Our test information function, this is like our item information function, but now we stack them all up for all of our items. So now we have information, where we know information about persons, and at a theta of 0.1 is where we maximized our information. We know the most about people that are around 0. So if you have a 0 ability, we would know a lot about you given this test. Whereas if you had a -3 or +4, we would know next to nothing about you. Because a person with +4 would get all the items correct. How do we know they're not at 5 or 6? And a person with a -3 is probably getting all of the items incorrect. So how would we not know they're further down that scale? And even taking guessing account, someone at a -4 or -10 probably has the same chance of getting the same items right just by guessing alone. So we don't know much about those types of persons. A test information function. Here's an example of another realistic test information function with 8 items. We know the new test, we maximize information has changed. So now, instead of being around 0, we would know a lot about persons that actually have a very low trait, probably around -1.5. The conditional standard error of measurement for that same test is we're going to see that just like our item information functions kind of like looks opposite of that. We have the least amount of error around people where we know the most amount of information, and we have the most amount of error where we know the least amount of people. So in our previous slide, we saw that it maximized around information around -2.5. So we can just eyeball and see that we have the least error around those people. Whereas when we go all the way up to a +4, we're going to have lots of error around those persons because our test may not be capable of precision around people with those high theta levels. And it changes. One important element we discussed earlier is that the standard error measurement changes depending on where someone's where someone is on the underlying continuum. Here's a distribution of a full test of theta values. So I've just took persons and plotted them here in a histogram. These are their theta values, most of them around 0. We see some deviation. Here are the items. The items are relatively easy in general. When we overlap those distributions, we can see that blue are the items. They're easy relative. They're in the negatives. Persons on average are around 0. So people are getting most of these items correct. Person ability, theta in black here, is around 0 or above. And the items are easy. So for this group, but we still end up mapping, regardless of hard or easy, if the model holds, we end up mapping our item characteristic curves well. There's many models we can use, many models we can extend that I would talk about in a more advanced course. These models could be a 4 or 5 parameter model. We have polytomous models. We have non-parametric models. We have multivariate models, mixtures, hierarchical models. There's many item response theory models that we could use. And really the whole idea of item response theory is merging with other latent modeling like structural equation modeling to get very complex structures when we want to relate how underlying abilities of or how underlying latent variables relate to each other. And you can put this in a Bayesian framework as well. Some examples of tests using item response theory. Feel free to pause this and look up some of these tests and some of their characteristics. Many of these have their information, obviously all of these have their information online. In this general introduction to item response theory, I tried to give you some of the mathematical underpinnings and ideas behind theta and item difficulty. IRT is extremely useful. We have lots of applications in large-scale testing, computer adaptive testing. So when we want to draw different items or sort of do equating on the fly, item response theory gives us parameters to help us with those computations. Auto item generation is very efficient with using item response theory. We can do differential item functioning and item banking. Many of these things are in those textbooks. You could look for further information in the textbooks that I had recommended. You can also take my item response theory course and probably look for future item response theory videos that I would put out. Further questions about IRT, we can look at some of our textbooks. You can take courses or look for further future videos from myself and others. For my students, please feel free to ask questions in class. This video was intended just to give you a brief introduction of some of the mathematical underpinnings. We didn't go over estimation methods or some detail about model fit. That's going to be in a full item response theory class and maybe some future videos that I put out. But certainly if you're more interested, item response theory gives us a very useful framework for moving forward for all of those things that we would like to do in assessment, both in educational assessment and psychological measurement as well. Thank you for watching.